at the beginning of the recording, at the beginning is usually me going over the quiz. So, you know, if you're not, just sit and listen. But if you're not sure about what you wrote or what you wrote on it, whatever, you could re-listen to the recording if you needed to. Distinguish between the terms anatomy and versus physiology. Who would like to say what they did, what they said? Nobody. Or you have to say it loud so everybody hears. Anatomy is the study of what? Structure. Structure. Physiology is the study of function. Y'all like that? I like that. That would have been short and sweet, and that would have been correct. Organs are composed of 2 or more tissues, and cells come together to form tissues. Cells come together to form tissues. Okay, great. So you have to be able to think about it like that. Briefly, and I do give partial credit for questions. These questions, numbers 1 through 10, are worth 10 points each, but I give partial credit, so don't leave blanks. Sometimes you might think to yourself, I don't know, but I know something. So write it down. Write it down, because I can give you some partial credit sometimes, right? Briefly explain what the theory of evolution states, and what I wanted you to put is that this states that the percentage of traits within a population will change over time. That's what I want you to put. And I really want you to understand what each of those little phrases mean. But that's what it states. Okay, great. List the 5 steps in order of the scientific method. And they are observation, question, hypothesis, test, and results. Great. Define the following terms. Auscultation. What you put? To listen. Is to listen, right? And gross anatomy. Yeah, what you can see with the naked eye, what you can see without a microscope, right? So what you can see with the naked eye. Palpation. Touch. So that doesn't take long to just write this first thing. Briefly define and explain. I can see where people could maybe get wordy in this. Briefly define and explain homeostasis, and be sure to name the type of feedback used in any organ systems that are needed. What I would have briefly wanted you to say is homeostasis means you're staying in a state of balance within normal parameters. It takes the nervous system talking to the endocrine system. And the feedback is negative feedback. And you could have probably said something about negative feedback meaning the initial stimulus that's received will be reversed. Whether it's high, it'll go low. Whether it's low, it'll go back high. Okay, good. Write one of the main premises of the cell theory. I gave you 2. The first you could have written was that life comes from pre-existing cellular life. The second one could have been that the smallest unit that has properties of life is a cell. So one or the other, right? Maya, Brianna, y'all have questions? Did you like that question? I mean, I'm just asking because if y'all have, if there's anybody that hears a question and I'm hearing them talk about it, it means that they may have had issues. And if there's an issue with the question we didn't talk about it, I'm gonna throw it out. So far, are we good? Did we talk about all the ones so far? All right. And I will throw it out, won't I, Jamie? I do. Give an example of an organelle. Mitochondria, nucleus, Golgi. I just wanted one example, but that's an organelle. Are organelles alive? No. But inside the cell, they have very specialized functions, but they're not alive on their own. They're not. Who's considered to be the father of medicine? Hippocrates. The microscopic study of tissue is known as what? Histology. It's known as histology. And what exactly does DNA stand for? I needed it to be spelled exactly right. Deoxyribonucleic acid. If it were, because I think I asked y'all to do that, right? Google that, make sure you know how to spell it exactly right. It's that important. It is that macromolecule that is the signature molecule of all life. It dictates everything that's going on inside of cells. When you became a zygote, okay, if there are people talking, they're pissing people off behind them. I can guarantee you. or in front of them? How many of you been in a classroom where that's happened to you? Okay, so let's don't do that to other people. I'd love for you all to talk, but I want you to have the whole floor so everyone can hear you when you talk. Otherwise, you are stealing people's time. Don't do it, okay? But if you have something to say, I'd love for everybody to hear it, right? So great. So DNA, when you were a zygote, and I could have asked y'all what a zygote was. I could have asked so many things. So many of you knew an embryo, a fetus, a neonate. You knew what all that was. Might you see that on multiple choice test questions on the first test? Yes, you did not study in vain. Students who think that they say, and they'll say to me, well, I overstudied. Please don't ever say that. That can't happen. It doesn't happen. You can't have overstudied. And you can't even have studied the wrong things, because you all know in here that everything you study, you will probably see it again tested on a multiple choice test, right? Nothing's wrong and nothing's overstudied. The crux is that you might not have been lucky enough to have gotten the questions today that you knew more than this showed. But in the wash, after 30 plus times that we meet and have quizzes, and it will be that many, it will, well, it won't be that many in this session, but anyway, it'll be, well, will it? I don't know. It'll be a lot. But anyway, it'll all work out and it'll even out. So don't get stressed about it. Take that copy and make sure if you missed something or you didn't have something clear, it's not a big deal, but just figure out what you need to do. Right? Right. You know, that whole classroom management thing is the same reason phones can't go off. Because anytime a phone vibrates, some of you have people in your classes where the phones are going off and people are getting up and leaving. Those people don't understand the basics of respect for their peers. So I just want to make sure that we all of us are in here, and time is so valuable to you. And that your time is going to be worth it being in here. Any questions about this? Oh my goodness, you didn't get an extra copy when I'm sitting there. Okay, so did everybody else get an extra copy? All right. Okay, great. And again, I'll try to have it straightened by late this evening, by night, and we will try to have that done. So we're going to continue on this morning with our study. Thank you. If you'll close that door, I appreciate it. All right. So, does anybody have anything they'd like to bring to the class's attention? That's a topic that they want to, you know, related to A&P. Related to A&P, they'd like to bring up. Anything? Any questions? Concerns? All right. If you think of them, just get my attention. Yes. You gave it to me. Okay, well, we'll get you another one because I am going to want you all to do something with that. Is it Chris? Okay, I'm going to get you to do another one because in the beginning of lab, I'm going to get you all to do something with those and hand them in. But it's okay. I'm mostly using them just so I can learn people's names quickly, right? Okay, so let's go ahead and continue our discussion because it is a discussion. We said lectures really kind of don't work, but unfortunately there's so much to cover. I really do feel like I need to try to give it to you all instead of making you just have to read it in a textbook. Could you all have talked to me this morning about positive feedback? Could you have told me the few times in the body where positive feedback is used? Could you have explained that positive feedback, you cannot stay in it for too long, because then that would take you out completely out of homeostasis, right? So y'all knew so much more than this quiz did, and I don't want anybody stressing too much about how they did on it. I would like to say this. How many of you have, you know, because I know y'all have so much time. I know you don't. I know time is so valuable to you. But how many of you got to go on to the visible body, register, put your course code in, and see your assignments? Is anybody yet? Is anybody? And it's only one person, Kelly. So you got to, good. And we'll talk more about it. I'm going to talk more about that at the beginning of lab today. It wasn't assigned for y'all to do. Y'all don't have to do it until today. No, you have until the beginning of next week. Go ahead and get that done and get on that. But it has that visible body has some great little exercises that help you with pronouncing some of these really kind of difficult words, right? This is a foreign language to most people. Do any of you feel like this is a foreign language to you, some of the stuff that we're talking about? Nobody does. Okay, great. We're all good. All right, good. Well, let me just share with you, when I was where you are, I felt like I was in a foreign language. And I would have really loved technology that I could have, on my phone or wherever, I could have clicked a button and heard how this word that I'd never seen before, heard before in class, how to pronounce it. And I could have practiced, how to pronounce certain words, but also looking at prefixes, root words, and suffixes and understanding that, oh my goodness, if I just, big words aren't big words. You know what they are? They're composed of a lot of little words. And so if you can learn prefixes, root words, and suffixes, you have it made here because the meanings of them don't change, right? So please know that. Please understand that. And we will have an exercise. Our second lab, our first lab quiz will be scientific measurements, right? And I've given you all an example of the first quiz. You have that as a practice. But the second quiz is going to be some medical terminology and some other things. And this visible body is just the best resource tool I've ever seen to help you with that. But we'll get there, okay? But please realize you cannot really be articulate in this profession until you know the medical terminology. Has anybody had medical terminology already? Raise your hands high. That's going to help you so much. That's going to help you all. Now, it's not a requirement to have that before you come into this class, but the people who have it, sometimes people are taking it in the same semester. Is anybody taking it right now? Taking it right now? Nobody. But they'll say, oh my gosh, this really helps me with medical terminology. Medical terminology helps me with this, so it's really nice. It's not required that you have it before now. It just means that if you're unfamiliar with terms, it's up to you to make sure that you get the terminology, the language. Okay, so, and being able to pronounce things are so important. You all have in your textbook, things that are called deeper insights. And I want to bring this one to your attention. It's in chapter 1. If you have your book out, that's fine, but you don't need to. You don't need to get your book out. I'm just going to tell you that at the beginning, because I'm going to show you, I'm going to hold this up. At the beginning of every chapter in this textbook, which is an amazing reference, and if you, when I say mature students, it has nothing to do with age, and it has nothing to do with intelligence and whatever. It means that students who understand, if they have read the material before the lecture is so much more powerful to them. Even when they read the textbook, they might have thought that they were like, oh my God, I don't get that. And I just, whatever. Even if you skim through it and read it, it can help you with lecture. So you all should be reading these chapters before we actually talk about them, right before we talk about them. And then hopefully my lecture will be more powerful. When we get to the test, the first test is going to have 3 or 4 chapters. I haven't decided how many, but 3 or 4 chapters on it. When we get to that first test, I'm going to remind you all that your test, certainly the questions come from our lectures. And you all were ready for that today, right? So you just have to review the lectures. But for a test, you have to go back to the chapters and look at the deeper insights on your own. These deeper insights you're going to be responsible for the basics of them on your own for the test. And there will be multiple choice questions that I take from these deeper insights. This medical imaging, if you would look, this medical imaging is one of these deeper insights in chapter 1. And most of these deeper insights are a paragraph long. They're not very big. It's not much to read, and you just want to read it and get the gist of it. But this one happens to be, actually 2 pages long with mostly pictures. But I do want you to look. You'll be responsible for these for every test, right? The medical and the deeper insights. Any questions about that? But if I talk about them in lecture, you would also be responsible for them for the next lecture quiz. Isn't that right? All right. Are there any questions about that? All right, so good. Everybody knows now what a deeper insight means. May I hold this open just for a second? Thank you. Caitlin, right? Caitlin. So, medical imaging is referred to as like non-invasive medical imaging. And you know, I'd have to kind of disagree a little bit, because when we think about things that are non-invasive, it means that they wouldn't be invasive to the person at all, and there would be no damage at all to the person, right? And they are considered to be non-invasive types of procedures because, you know, they're not much risk to them. But one of the things that y'all all know about are x-rays, don't you? Everybody has heard about that. Has everybody here had an x-ray? I was just trying to think if I've ever had an x-ray. I haven't. Oh, well, dentist. Okay, that counts. That counts, doesn't it? But I've never gone and had, okay, so dentist. Is anybody going into that? I consider that a whole different field because, oh my God, I start sweating just thinking of your appointment. Okay, but I don't think I've ever had like other things. But dentist, absolutely. But anyway, so x-rays are these flat pictures that we can get of something. So we, you know, most people understand you can see whether there's a broken bone or whatever, and so they're really kind of nice. Now, some of these other procedures that y'all have heard of, and I know you're going to read that deeper insight before the test, but some of these other things that you've heard about, they're not quite so non-invasive. Some things require that you actually infuse dyes, or that you infuse radioactively labeled substances. Now, it's hard to call that non-invasive, isn't it? But anyway, it's usually very low risk, and it gives a lot of information. So what I want you to know just from lecture today, and then I know y'all are going to read a little bit more about them for the test, but from lecture today, I just want you to know, because you've all heard of CAT scan or CT scan, and you've all heard of an MRI, and you've probably all heard of a PET scan. So for today, I want you in the notes to just make sure that you know what those things stand for, okay? So CT scan stands for computed tomography, and most of these CT, MRI, PETs, they give a three-dimensional look rather than that X-ray that's flat. It's going to give a slice that helps to give this three-dimensional look. Because are we flat? No, we are not flat. And so it's nice to have that three-dimensional analysis. So CT stands for computed tomography. A PET scan is introducing radioactively labeled glucose into the system. So that has to be injected. But this stands for positron emission tomography. And again, this is so nice because it lights up the different cells and how what's going on with their metabolism. So a PET scan, positron emission tomography. I know y'all can go back and look at this. It's in your book. And for right now, you're just going to know what those initials stand for. MRI is a magnetic resonance imaging that can be used. And, you know, whatever. So this, and sonography, ultrasound, is using like these waves, these sound waves that bounce back off to give imaging, right? So sonography or ultrasound, which is, you know, you really kind of consider this not as invasive as something like the MRI would be, or the positron emission tomography. So anyway, we're just knowing basics about them and what they stand for, okay? Any questions about those deeper insights and what that means about those deeper insights? No? Okay, so let's see if I can find this chapter 2. All right, before we actually, guess what, guys? We finish our introduction and we can begin our study of human anatomy and physiology. And where did y'all say you want to start? Do you want to start with the organism? Do you want to start with organ systems? You do want to start with organ, but what do you have to know about the organism? You have to know what systems. The organ systems. Wait a minute. But for organ systems, you have to know the organs. Wait a minute. For organs, you have to understand tissue types. For tissue types, you have to understand cells. For cells, you have to understand what's inside cells, right? And it only makes sense that we start at the atomic level with atoms that make up molecules. What did we say that is the study of? That's the study of atoms of elements that make up molecules is chemistry. How and why they play together, how and why they play together and why they won't sometimes is called chemistry. I want to give you all a definition of biochemistry. The word is biochemistry. What do you think that is related to? What do you think biochemistry is related to? Because bio as a prefix always means what? Life. It means life. It means life. And chemistry, the ones that make up living things. You guys, how many of you remember the periodic table? Hopefully nobody made you memorize it because the reason we have the table is that we can go to it. You know, so we don't want to memorize things that we have tables for. But you remember the table, don't you? And you remember learning things about that periodic table. And you remembered that there are quite a few elements, right? Does anybody remember how many there are of elements? Which are they each get their own little box on that table, don't they? And they're in columns and they're in rows. You remember that? But anyway, you remember each box represents an element, right? Does anybody remember roughly how many there are? I mean, are there like 10 or are there? So there are over 100, and some of them are man-made. And these elements represent everything that we know in nature, including non-living things. What's in our atmosphere, what is in the earth, you know, inanimate surfaces, but then certainly also living systems. Biochemistry is the study of the elements that make up life. And there's only 24 of those. There are only about 24 of those that make up living things. So of the over 100 some, we've narrowed it down a lot, haven't we, when we think about biochemistry, studying the elements that make up living things. I want to let you know something, Andrea. And I love the name. Andrea. You and Ashley with an I. And you and Ashley with an I. 24 plus elements. That makes just like, don't write it down, just look at it. That make up living things. Is that right? We're all like that. We have that in common. And these are elements that are coming together to play and sometimes sort of fight against each other to make up you and all of us. 98+% of us are really worth 4 elements. I want y'all to think about like Legos and building blocks, right? So if you had different Legos, look at the diversity in this room right now. Look at the diversity. Are there any 2 of us that are exactly alike? Do you see a ton of diversity? Isn't that amazing that all of us are made mostly of 4 elements? 98+% of us are made of 4 elements, and because of the differences of how they're coming together to play or not, we're seeing all this diversity. If that doesn't blow your mind, you weren't listening. Who couldn't be interested in chemistry and understanding how and why those elements will play with each other or not? The 4 elements that make up most of a living organism are, and you can abbreviate them because they're abbreviated on the periodic table, aren't they? They are hydrogen, oxygen, carbon, and nitrogen. Those 4 elements. Guess what, Andrea? 98+% of you, look at you, amazing. I could pull your hydrogen out. I could pull your oxygen out, pull your carbon out, pull your nitrogen out. and put them in, some of them need to go in tanks, some of them in beakers. But I'm going to tell you something. I could sell them to the chemistry lab for a few dollars. A few dollars. You're telling me that elements, those building blocks that make up Andrea, a few dollars, but how they're coming together to play and interact in her living cells and systems, this is priceless, right? Y'all, that's chemistry. So who's excited about learning chemistry? Who's excited? Well, lie to me. Because actually, it should be. And you should understand that I told you that those atoms or those elements that make up all living things, it's at that molecular structure. Structure dictates what? It's at that molecular structure when things go wrong in the cell, molecular and cellular, that causes all what? Disease. You may know somebody that has a disease and you may spout out diseases, whether they're inherited or a disease that is infectious or whatever. But guess what? If you don't really know what it is or understand it or could possibly know why somebody's being treated for the way they're being treated, unless you really understood what was going on with that disease at a cellular level. So many students want to come in, and this is just human nature that we want to come in and we want to see, we don't want to know the normal, we want to know that gross stuff, you know, like tell me the bad stuff. We can't understand it unless you learn the normal, right? So we're going to learn what's normal, and then you understand when things go wrong, what those normal things were supposed to provide. And so when something goes wrong with that, what that individual has lost, right? So this is what we're going to do in chemistry. But before we start that, we've already started, because you all have 4 things written down that you know are the predominant elements in biochemistry. I actually do want to go to this because it's in front of me. The deeper insights in chapter 1, which is really just our introduction to this whole thing. These deeper insights. A couple of things that are actually that we've maybe already talked about. But I want to let you know, you'll see in one of these things something about vesicle organs. Does anybody know what a vesicle organ is? Does anybody know what a vesicle organ is? Did you know that every one of us are sitting here with muscle? We have muscles that can raise our ears, raise them. I'm having to pull my muscles don't work to do this, but they're there. They're there. We have muscles that can raise our ears and point them forward. Now, those muscles no longer work the way that they would have. We have organs like our appendix that in comparative species is part of the immune system, but right now doesn't function in humans, has lost its function. We have organs that we know no longer really function, but we still have them. These vesicle organs are actually evidence of what? Evolution. They're evidence of evolution. Because do you think they never worked? Wouldn't that have been inefficient that we have things that never had worked? But the percentage of traits found within the population have changed over time. You will still find on rare occasion people who can really raise their ears. Do y'all know anybody who can do that? But most of us, they cannot work. And I don't think there's really anybody that can move their ears forward. But why would that have been a good thing back in the day? Because hearing was going to be important for hunting, but also survival. Because not only would you be able to maybe hear the prey, but you would be able to hear the predator, right? So that would have been a very important survival thing. We don't have it anymore. Every one of your hairs, I want y'all to think about, do you realize that almost every part of your body has hair follicles and has hair? Almost every part, almost, right? Except for certain things. But we have hair. Some of us have kind of childlike hair, and that some women carry that kind of childlike hair like I do, where you can't see anybody's hair. Like you could see it if you looked really close, though. You could see it. So there's hair everywhere. Every one of our hairs have its own muscle that can pull that hair up. Now, do you think all of them are working? We still have some that work, and what do they give us? Goosebumps and chill bumps. But most of them don't work anymore because we really don't need to raise all of our hairs to stay warm and or to dry off and or to whatever. But all of our hairs had them, right? So these are just examples of vestibular organs. Another thing that this, a little thing, and I don't think I even ever asked you a question on the test about this one, but men in an oven, you know, when we talked about what are characteristics of life, if we took a cow and we slaughtered that cow for meat, and then we had a steak laying here, right? Obviously, that muscle tissue in that cow is no longer alive. It was alive, but now it's no longer alive. So they talk about this man who goes into this dry oven with his dog and with the steak, right? Or at least I think that's what they talk about. But anyway, so what happens as the temperature is getting hotter? The man is going to do what? The dog is going to what? Pant to get up to try to cool down. And the steak is going to cook. Because living things can respond to their environment, can't they? Living things can respond to their environment and hopefully change things to stay in what? Homeostasis. Where non-living things cannot. Right? So that just sort of reinforces these clinical insights. Sometimes I don't get to cover things in lecture of these, but no big deal. Y'all are going to read them before your first test. Any questions from these, if I didn't talk about them in lecture, will be multiple choice questions, very kind of basic, nothing picky, you know, types of things. Fair enough? All right. Okay, so now we're back to chemistry. I did want to introduce you to those deeper insights. All right, so we're back to chemistry, and you know, here's what I want you to know about chemistry. I want you to know I don't like their notes. I don't like their notes, and so I'm going to write my own. All right. So here, and I want. Is there anybody in here would say that? Well, whether you liked chemistry or whether you didn't like chemistry, I hope if you had any prejudices against chemistry, you left them outside. Because I want you to know that I'll only question you on things that I give you in here, right? So just try to start fresh, and let's see if we can get the basics of what we need to know about biochemistry going forward. I want you all to know that elements, those boxes on the periodic table, atoms of elements, atoms of those elements are the smallest things that we know that have their own unique properties. So carbon is a very different element than hydrogen, right? And hydrogen acts very differently than oxygen. And oxygen acts differently than whatever the last one was. But anyway, we know that. All right, now, but there's some things that are, I hope I can write on that. I might have to go back. But anyway, there's some things that are unique to atoms of these elements. Some things that are things that we need to know to be able to understand why and how some of these atoms of elements play or not. So I want to start you all off with some basics. In the center of, in the center or core or nucleus, am I interchanging those terms? Center, core, nucleus, right? Of an atom. In the center, core, nucleus of an atom, you will find these subatomic particles that are called protons. I've used that little thing to call them protons. And I want you to know that protons are always found in the what? The center, the core. And I'm going to want you to know that protons actually always have a positive electrical charge. They aren't wishy-washy. They have a positive electrical charge. And when I talk about an electrical charge, guys, I mean an electrical charge. Okay? So anyway, and they're always going to be found in the core, in the nucleus, in the center of an atom. The number of them is so important. The number, how many numbers there are, it's so important, that number, in understanding how that atom is going to act, that this is actually called the atomic number. So if I were to ask you, how do you determine the atomic number of an element, what would you say? The number of protons. Fair enough? Is that fair enough? Anything scary so far? Anything scary so far? Yes. Okay. Protons are found in the core. They have a positive charge, electrical charge. The number of them, how many there might be of them, is so important, it's called its atomic number. So for this example, and remember, this is just an example I'm drawing, but for this example, what would the atomic number of this atom be? 6. Yeah, really? 6? Are you right? Right. So this example of this atom, so far, has the atomic number of 6. So I realize that's going to be important, and I'm probably going to learn more about it in just a bit. And so I'm going to stay tuned. Everybody good so far? All right. Now, something else that can be found in the core, in the center, in the nucleus of an atom is another subatomic particle. They're called subatomic because the atom is the whole thing, but what's inside of it, right? Another thing that can be found there is something called a neutron. A neutron is a subatomic particle that has no charge. Does everybody know that this symbol means none? Has no charge. Are we good so far? Where are they going to be found? Where would neutrons always be found? In the nucleus, in the core. All right. All right. Now, I want to let you know something else about protons and neutrons. For every one of those, there's one atomic mass unit. So for every proton and for every neutron, for every one, each one has the weight. Now, it's not really weight, it's called mass, but you can think of it as weight. Has one atomic mass unit associated with it. So every one that's there has a 1 weight. Fair enough? Is that all right so far? All right. Now, for this example of one atom, of one element, for this example, how many protons did y'all say there were? And how many neutrons did I draw? 6. I drew 6, right? So for every one proton, they had one atomic mass, and for every one neutron, there was one atomic mass. So for this example, this is just one example, but for this example, how do I figure out the atomic mass of this atom? I would do 6 plus 6. And 6 plus 6 is what? 12. Anything tricky so far? Are we good? All right. So that's how you determine the atomic mass of the atomic mass of an atom is determined by adding the number of protons to the number of what? Neutrons. Good? Yay. Yay. All right, now I have something else. I have one more subatomic particle I need to talk to you about. And I'm about to tell you in the next 10 or 15 minutes everything you really need to ever know about biochemistry. Don't tell a biochemist I said that. But it's really true. And it's going to explain chemistry to you. I promise you it is. You ready? All right, there's one more subatomic particle that you need to know about. So far, we've only talked about what part of the atom? The nucleus, the core, the center. And so far, y'all know that core has an electrical charge. What does the core have? What kind of electrical charge? Positive. What do y'all know about electrical charges? What kind of charges attract each other? Opposites. You know that opposites attract? All right. So I need to tell you about one more subatomic particle, and I need to tell you some unique things about it. Nothing about it's tricky. You just need to be listening, okay? I'm trying to stay up and listen. But what I want to tell you is that because of this positive core, it's attracting negative subatomic particles. And these little negative subatomic particles are actually called electrons. And I want you to know that electrons have a what charge? Electrons have a negative charge. That's a little negative charge. They're so light that they have no mass. They have no mass. They're so light. You can think of them as like flies at a football arena, a professional football arena. The professional football arena is the core, the positive charge. And the fly, the little tiny fly on the outside of the stadium is an electron. They're tiny. They have no atomic mass. So they contribute nothing to the weight of an atom. But they have a negative charge, so are they being attracted to that core? Are they? Let me tell you about these little flies. They don't sit still. They are so fast, and they're orbiting the core. So I drew this like this, but we understand that they're actually never really at a, well, they're at points, but it's hard because they're just swarming. They're swarming so fast that they form not just an orbit, but almost like a cloud. They're moving so fast. Have you heard of these as orbits or clouds or shells? Have you heard of that? And the reason they're called that is because these little electrons are going that fast, right? You can picture that, can't you? Let me tell you some little, these are laws of nature. This is not beliefs. These are what we know happens with atoms. Close to the, what was this? Close to the nucleus in that first orbit. What's another word I could use for orbit? Cloud or what? Okay, cloud or shell. In this first orbit, there can only be a maximum of 2 electrons. A maximum of 2. There can only be a maximum of 2. So I want you all to tell me right now, look at this and see if this makes sense to you. See if this makes sense to you. What did y'all say this core has as far as a positive charge? As far as the positive charge, 6. That number is so important. It's called the what? It has a positive charge of 6. So yeah, it's attracting 2 little negatives, but do you think it can attract more? How many more? 4? Where are they going? They can't be in this one, right? So they're going to be in the second orbit. The second, and let me just tell y'all, I'm just going to write orbit. But the second, third, and fourth orbits, second, third, and fourth, can hold up to a maximum of 8 electrons. A maximum. Well, yeah, so the second can hold 8. The third can hold 8 if there's more than, and the fourth can hold up to 8. And they can't hold any more than that. Any more than that would have to bump out to the next one. Are you with me? So I want you to think about me as this atom. I get to be the core. I'm the mom. I get to be the core. I have a 6+ charge. That means I have 6 children that are wild. Because are those electrons going fast and crazy around me, orbiting around me? How many do I really have up close, though? How many can I really control? 2. I can kind of control 2. Any more than 2 are going to bounce out. And you're telling me that I have 4 more. So they bounced out to what orbit? The second one. They bounced out to that one. And do I have as much control over that second orbit as I do the first? As they bounce out, electrons, they get crazier. They get more active. You get what I'm saying? And that just is a law of nature. We know that happens. For this example that I gave you, this one example that I gave you, and by the way, the second, third, and fourth orbits, this maximum of 8, I want you all to know is called the octet rule. Octet. What do y'all know oct means? It's called the octet rule, that they can only hold. Now look, I would, you know, if this was true, we had all semester with chemistry, we would talk about all of the elements on the periodic table, and we would talk about elements way beyond the size of the ones in biochemistry. But the fact is that this is enough for us for right now, as long as y'all get what I'm telling you, right? All right, because I'm about to add to it. So y'all said I haven't really finished drawing this yet, have I? Because you said it has another what? May I erase this? May I erase this? Y'all said it has another what? It has another orbit. And even though we know this orbit isn't really like a solid circle, we know that this is just representing the pathway, and it's 3-dimensional. How many did y'all say? How many electrons would be out here in the second one? What you said? It would be 4. It would be 4 of them out here. Now wait a minute. For this example of this element, what is its outermost orbit number? Second. Y'all said for this example of this atom, of this element, the second orbit is its outermost one. And is that right? Somebody said no. Are we good? This was the first orbit that had 2, and this second one, they had to bounce out. Those 4 had to bounce out. Let me ask y'all something. Is this outermost orbit filled? No. Why not? Because it can hold up to 8. So how many more would it like to have? 4. It would like to have 4 more. So it's just not filled yet, right? Is that right? All right, I want y'all to write down the word valence. V with a V as in Victor. I have people misunderstand me and write V and whatever. Valence with a big V as in Victor. And I want you to know that word means outermost. And I want you to know that sometimes people ask you what is the valence orbit number, and that's asking for the orbit number, right? But sometimes you get asked what is the valence electron number, and that's asking you what, Kelly? Which orbit? Because what does valence mean? Outermost. So if I were to ask you all what are the valence electrons number in this one, what would you say? 4. And if I ask you what is the valence orbit, you'd say, and if I ask you if that atom is filled or not, its valence orbit's filled, you'd say no, because you know the octet rule says the second, third, and fourth would need 8 to be filled. I'm going to give you all the explanation of how and why atoms of elements play or not right now in this sentence. You ready? You ready for it, Jamie? Atoms of elements play to complete their valence orbits. Atoms of elements play with one another to complete their valence orbits. Kristen, is this atom of this element going to be a player? Why do you think? Is its valence orbit complete? It is. Its valence orbit number is which number? 2. It's the second orbit, and that orbit can hold up to how many? 8. And does it have 8? It has how many? So is it going to want to play? So it's going to be a player. Do you get that? It is going to be a player. Let me tell you about this atom I just drew for you. This is carbon. And I want you to know that carbon, this is what carbon looks like. It has the atomic number of 6. And most of the atoms in this element look like this. Not all of them do. But most of them, they have 6. They look, for right now, for your information, they look like this. So let me tell you about carbon. because it has that, it's going to play with another valence electrons on this atom, this element, and this one over here. It is going to play on all sides. I'm going to tell you something. It's going to play with oxygen. It'll play with hydrogen. It's going to play with anything that's going to help it to fill its what? Its valence orbits. To make its valence orbit seem filled. Because atoms play to do that. To fill that. Let me give you another example. If I told you something has the atomic number of 1, what did I give you? It has the atomic number of 1. What did I just give you? I gave you what was positive, and that's the proton. So I'm going to draw this little example of this atom right here, okay? Is that right? Did I do that? If I told you it has the atomic mass of 1, what do you know is not here? A neutron, because it only has 1 proton, right? Because if I give you the atomic mass, you know how many protons. I mean, if I give you the atomic number, you know how many protons. If I give you the atomic mass, you know how many neutrons. Is that right? Now, let me just ask you something. You said the core here has a 1+ charge. So what do you know might be found circular going around it? A what?
Electron.
An electron. Why would that electron be near there? Because it's a little negative thing. It has a negative charge. And where would you find that? In which orbit? The first orbit, and you said, well, I should have made it blue. But the first orbit, and you said that little electron would be just orbiting around. Let me ask you something. What is the valence orbit of that example?
1.
What is the valence orbit number? 1. What is the valence number of electrons in that? 1. Is that a happy atom?
No.
Why not? Because it wants its valence orbit to be complete. Are you with me on that? Let me give you another example. So let me tell you what this is. This is hydrogen. Hydrogen's a player. Carbon's a player, aren't they? They're players. Let me give you another example of something that has the atomic number of 2. What did I just give you? There's 2 protons here. There are 2 protons here. 2+ charge. Let me ask you something. How many electrons are circulating around? 2. Let me ask you something about this atom. Is it a player? Why not? Because its valence orbit is complete. It's not a player. If y'all remember the periodic table, that whole list of that column on this side, this is helium. That whole list are called inert because they don't have to play. Why don't they want to play with anything else? Because they're satisfied. They are satisfied. Their valence orbits are complete. They don't play. They don't. But hydrogen that I had drawn for you before is a player. Carbon is a major player. Carbon will play on all sides. I want you all to know that carbon is the defining element of organic chemistry and organic life. I want to say it again. Carbon is the defining element of all life on this planet. It is. It's the defining element. When you talk about organic chemistry, you're talking about molecules that have a ton of what? Carbon. And let me say this. It makes perfect sense to us that our fats are huge chains where carbon is the backbone of the chain. It makes sense to us that our carbohydrates are these rings that have carbon forming the rings, because carbon plays on all sides. Remember, these atoms are not flat. They're 3-dimensional. If atoms were flat, you'd be flat. They're not. They're 3-dimensional, aren't they? And carbon is that defining element of all organic chemistry. Now, I want to have you all do something. Then we're going to take a little break. All right? So I want y'all to play this game with me. I want you all to tell me, and if you're not getting this right now, it's fine. But I got to listen to the recording again if you can get it, if I end up being able to put it up. or get notes from somebody else, or read the book. Because I'm not making any of this up. I'm just trying to explain it to you in a way that I think is easier than the textbook, but you got it in your textbook. All right, so I'm telling y'all that something has this atom of this element has the atomic number of 8. What did I give you? So there's 8 protons, right? Don't make me draw 8 stars, okay? But there are 8 protons. And if I told you it had the atomic mass of 16, what did I give you? 8. So there's also, in this particular atom, there would have been 8 neutrons, right? Neutrons that have no charge. By the way, the neutron number only changes the mass. It doesn't have anything to do with the chemical reactivity of an atom. It just changes the mass. All right. Now, so everybody's good so far. So y'all tell me, explain to me what the orbits would look like for this atom. Tell me what the orbits would look like. The first one has how many? 2. Why not more than that? Because that's all it'll hold. That's the maximum. Are we done? No. What do y'all want to do?
6 more.
You think there's 6 more? Where would they be found? And they would be found out here. Is that right? Yes. They would be found. And I'm drawing them here like they're stable, but are they? They're not. They're flying. They're crazy. They're flying so fast it looks like a cloud. All right. So have we finished really explaining this? All right, so let me ask you something. Which orbit number is the valence orbit for this atom? 2. And what's the number of valence electrons in that?
6.
Is this going to be a player?
Yes.
You think so?
Yes.
All right, because it's not complete. Its valence orbit isn't complete. So it's going to be a player. Let me tell you something. Y'all just told me about an atom that has the atomic number of 1, and you said it had the valence electron of 1. Did you say that?
Yeah.
And here's another one that has the atomic number of 1 and a valence electron of 1. And you remembered that these electrons are really flying, aren't they? So if this atom cozies up with this atom and this atom cozies up with this atom, is this atom feeling like its valence orbit is filled? It is feeling like it. It's feeling like it has 2 because it's sharing, isn't it? And is this atom feeling like its valence orbit's filled right now? Which you all just wrote was water. This is such a happy arrangement. So happy that the water that you drank in your coffee this morning is the same H2Os that were peed by the dinosaurs 65 million years ago. Right? Or like we are. Because this is a happy kind of a relationship. Why is it happy? Because what did you say is really, you can explain everything about chemistry and understanding that atoms of elements want to have their what complete? Their valence orbits. They want to have them complete. Right? All right. Now, are we good? All right. Good. And so great. What I'd like to do is take just a 10-minute break. We're going to take a 10-minute break. We're going to start back in 10 minutes. So be back, okay? And we're going to lecture a little more, and then we've got lab. All right. But anyway, let's take a quick break. Oh, come on. So I think we're back, right? Most of us are back, so hopefully we'll start back here. So again, just as like a motivation for maybe trying to spend some time and truly understanding chemistry, which elements make up life, how and why these elements do what they do, and as we progress through our study of chemistry, just motivations for wanting to do this. The old saying is that you are what you eat, and guess what? We are what we eat because we have to get the building blocks for the molecules that will end up making our cells, right? And those molecules inside of our cells determine how our cells function. And we really are just our trillions of cells communicating with each other and functioning as they should be functioning. So this gives you maybe just a little bit of motivation, this slide in introducing this. I was talking about the top four elements that make up most of any living organism, whether it's a human cell or whether it's a bacterial cell or a protist or a fungi or what. These are the four top elements. But then there are these others that we have what are called lesser or tracer amounts of these. What I'd like to do now is actually talk to you about something else. And again, I like my notes better because you know that saying about everybody knows in your own little mind. Anyway, it seems like to me it makes more sense to do this. Let's continue our just study or review of this, and let's see how much maybe we retain. Of course, we're just being introduced to it, so if you're not retaining it now, it's not a big deal. But let's try to do it collectively. If I told you something had the atomic number of 11, what did I give you again? 11. So there are 11 protons, and we know they have a positive charge. Is that right? So they're in the nucleus, they're in the core. Now the atomic mass, we said, would tell us how many protons plus neutrons there are, and I don't really even care about this one because we know the atomic mass doesn't really influence how the atom plays. But anyway, we could look that up on our periodic table, and we could look at it on the chart. And we'll talk about more about neutrons in just a minute. But for right now, let's see if we can figure this out. So how many electrons are they, and where would they be found? For this particular atom, this example of this atom. So where are they going to be found? And so in the first ring that we know isn't really a solid ring, it's just we're just showing that this is where the orbit would be. There'd be how many? Because that's the max. And what you say would be out here? 8. So y'all think there would be 8 here? Is that right? 8. I'm just doing them together so I can keep up with how many I've done. All right, so, but we know they're really just fine. So there's 8. So what you say? One more. You think there's one more? There's one more orbit with one more. Okay, so because this has an 11 positive charge. Right? Okay, so if I were to ask you about this particular element, this atom of this element, you would say its valence orbit is which orbit? Third. You'd say it's the third orbit, and you'd say the number of valence electrons in that orbit is 1. And to be complete, that orbit would need how many more? 7. 7. So let me tell you about some elements, some atoms. Some atoms of some elements, like, because this has an 11 plus charge, and that's a powerful thing. That's a powerful draw, but it's not powerful enough to pull 7 away. It's not. So I want to let you know that some atoms of some elements, like this one, will give up. They'll give it away. They'll give this valence electron away. Now, not all elements do that, but some do that. And the ones that will give away electrons are called ions. The ones that give away that whole valence orbit, the ones that give it away, they now have how many positive charges? How many positive charges do they have? 11. That didn't change. But how many negative charges does this one have? 10. So now it has less negative than positive. This atom is a positively charged atom. The whole atom is positively charged. And that whole atom that's positively charged is called a cation, because it has a positive, the entire atom has a positive charge. And let me tell you about something else. Hold on just a minute and let me tell you about something else. Let me tell you that this is actually known, this example that I gave you right here is called sodium. And on the periodic table, it's abbreviated Na because natrium in Latin means sodium. So it's just natrium. Natrium is sodium in Latin. So the reason you often see sodium with the little positive thing above it is because the atom has a what charge? It has a positive charge because it gave away what? It gave away that valence electron. Why did it do that? It couldn't pull in those 7 that it needed. That's just not a nature law. It would have done that. But also it gave it away because now what becomes its valence orbit? And is the second one filled?
Yes.
Is this happy? This is happy, just like this, because its valence orbit is now complete. It gave that electron away. All right. Now, wait a minute. Now, I want to tell you all about another one. And this one has 17. Are y'all going to make me write that again? Okay, so 17. This one this atom has 17 positive charges. So what did I tell you? What did I give you when I said that? It's what number? What number is it on the periodic table? 17, and that's its atomic number, isn't it? Right? Okay. So wait a minute. It's got 17, so now I need to make sure I got my electrons right. 2 will be in the first. How many are in the second? 8. And then, does it have any more? How many more does it have?
7.
You sure?
Yes.
You sure that it has 7 out here? It has 7. Is this a happy atom?
No.
Is this a happy atom?
No.
Why?
No.
Because its valence isn't full. So what do you think it steals? It steals an electron. It steals an electron. And now chloride has a negative charge because it only has 17 positives, but it has how many negatives? 18. And it's an ion too. It's also an ion because ion simply means that it has a charge, right? In this case, though, it's a negative charge, so it's called a what? An anion. An anion. So now, let me ask you something, see if this doesn't make sense to you. What kind of charges did y'all say attract each other? You said opposites attract. So at a subatomic level, it made perfect sense to you that that positive core, that positive nucleus, attracted negative electrons, didn't it? Now I want to see if this makes perfect sense to you. And listen to me. If an atom is a charged atom, we call it an ion, don't we? If that whole atom has a charge, what kinds of atoms will attract each other? Negative, oppositely charged ones. So sodium, you told me, has a what charge? And chloride, you said, has a what charge?
Negative.
Do you think they attract?
Yes.
They attract so much that you can shake them out of a container you have at home, I bet. And what is it called? And they attract each other so much if they're close enough together that they will form crystals. They will attract each other so much so closely together that they will form crystals. Are you with me? And you call sodium chloride salt. Let me tell you another word for ions that have charges. Another word for them is salts. But you know what another word is? Electrolytes. 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 So if I were to ask you what is another term for salts, you would say electrolytes. Have y'all ever heard that it's very important that your electrolyte balance be what it needs to be? Okay. Do you know why? Have you ever known why? What did you say?
Electron can cause other problems in your body.
So electrolyte imbalances can cause other problems in your body. All right, so let me tell you why ions, salts, and electrolyte that are called electrolytes are so important to your body. They are charged atoms that provide the electricity for your body. They're providing the electricity for your body. If I take the electricity out of your house, is much happening in your house? Is it?
No.
No. If I take the electricity out of your phone, are you doing much with your phone? No. These atoms in the right balance have to be present, or your cells are no longer going to be able to be living cells. Have y'all ever heard that cells have action potentials? Have you ever heard that? That cell membranes have a resting potential, but then they also have what's called action potentials. Do you know what generates that shock at the membrane level? Electrolytes are providing that electricity, that shock, and it's a shock. It's an actual millivoltage change shock. And it's being provided by what? Charged atoms that are called what? Also known as electrolytes, and also known as salts. We're going to talk more about it in just a second, but are you good so far? Are you good so far? Okay. All right. So I want you to know about another type of atom that can happen to some atoms or some elements. What did I tell you is the element that is the defining element of all living systems? Carbon. And I told you because carbon is a neutral atom. It's neutral. That means it's going to have equal numbers of what charge and what charge? Negative and positive. So that means it has equal numbers of protons and electrons. Is that right? So carbon is a neutral atom. That means to fill its valence orbit, it's going to be having to play with other atoms, close up to other atoms. And it's going to form these long chains. It's going to form rings. It's going to do all kinds of crazy things. And it forms these huge organic molecules that we know of called carbohydrates, lipids, proteins, and nucleic acids. We'll get to that. Don't write that down now. But y'all trust me on that, don't you? So a neutral atom is one that doesn't have a charge. The atom itself doesn't have a charge. So I want to, maybe you can recall in your notes that I gave you carbon as a 6 proton, and the one example I gave you had 6 neutrons, didn't it? And what did that mean when it had 6 neutrons? It meant its atomic mass was what? It meant its atomic mass was, atomic mass unit weight or units is this, right? All right, so it had that. But if you look at the carbon on the periodic table, you're going to see the atomic mass is something like 12 point, and it's going to be a remainder number that's really long. And that's what it's going to say its atomic mass is. And do you know why that is? When you look at periodic tables, how many of you remember in your high school or elementary school chemistry why that is? Why when you look at the elements on the periodic table and you see their atomic mass, there is this long remainder number. Does anybody remember why that is? The reason why, and you know guys, I'll go ahead and write the electrons for you just so I've got it kind of complete. But I'm not really talking about the electrons now, but okay. The reason you see that atomic mass number is being this weird number is because not all atoms of carbon have this mass. Some atoms of carbon have 7 neutrons. Some atoms, it makes me put that down before I go. Some of them have 8. The one that had the atoms of carbon, they're still carbon because what dictated carbon? The number of what? Protons. What is that? Okay, so, but some little atoms of carbon are heavier than others. That's all right. That's all right. Because it didn't change how carbon behaved, doesn't change how it behaves. The reason I want you to know that some atoms of some elements that have different mass, they're actually, and that means they have different number of what? Subatomic particle. Different numbers of what? Neutrons. Neutrons are the defining thing for what I'm about to tell you. These are called isotopes. Have you ever heard of isotopes? Some of you say no, but now you have. So write down isotopes. Write down isotopes. An isotope is an atom of an element that has an unusual number of what? Neutrons from the typical one. Does that make sense? It has an unusual number. Is this still carbon? Is this atom still carbon? Is it still going to act like carbon when it's playing? Is it still carbon? Yes, it is, but it's a heavier carbon, isn't it? What's the atomic mass for this carbon I just drew? It's 14. Would everybody agree? How did you get that this atomic mass was 14 for this atom? Because you added the protons to the neutrons. The proton number didn't change because this is carbon. But the neutron number changed, and so this is a what of carbon? It's an isotope of carbon. Now let me tell you something about isotopes. Most of them are just very stable, and they're not going to be changing. We have isotopes of lots of different elements, and they're very stable. C13, you'll hear about C13, which is carbon with the atomic mass of 13, pretty stable. C14 is not stable. And what that means is that if it's not a stable atom, it means that it's a radioisotope. Have you ever heard of radioisotopes? Have you? A radioisotope is defined as an unstable isotope, and I'm about to tell you what that means. You ready? A radioisotope is an unstable isotope, and I'm about to tell you what it means. It means that this core, the core is the what? Nucleus, is breaking down. And as this core is breaking down, guess what is going to be given off? Who said that? What is going to be given off? Radiation. Radiation is going to be given off. Can too much radiation cause damage to neighboring things? Yeah, we do know that. All right, so most isotopes are stable, and an isotope is simply an atom of an element that has an unusual number of neutrons. You good? But a radioisotope is not stable. It's unstable, and that means over time, what is breaking down? The nucleus. And what is given off when it's breaking down? Radiation. So I just told you all about PET scans, positron emission tomography scans. Anybody know anybody who's had a PET scan? So when they have a PET scan, they get injected with radioactively labeled glucose. And what they have done is tag the glucose in there with C14. So when somebody, y'all don't need to write all this down, I'm just telling you. We use radioisotopes in medicine all the time for radiation treatments, for radiation for diagnosis. In this case, in the PET scan, glucose is the molecule that's needed for energy for the cells. So cells that have taken up more glucose that they're breaking it down are going to be hotter. They're going to be giving off radiation. So when the person gets that radioactively labeled glucose and then they get scanned, the cells that are crazy active, really crazy active, are going to light up. What kind of cells do we know that require crazy amounts of energy? What kind of cells have lost their control mechanisms for metabolism and growth and mitosis? Cancer cells. Somebody probably said it, I've been here before. Cancer cells. They're going to light up. And even if there's just a few there, you're going to see them because they're going to light up. It's a really sensitive scan. They're expensive scans, but they're sensitive scans and are really diagnostic, usefully diagnostic. But also, we can tag iodine. We can radioactively labeled iodine can help to detect thyroid cancer because your thyroid gland pulls in iodide to make its hormones, T3 and T4. So there's lots of things that we can use radioisotopes for in medicine and for diagnosis, but should we be careful? Is there care with that? Yes, it is, right? Okay, so do you know what a neutral atom is? It's one that has equal numbers of what and what? Protons and electrons. Do you know what an ion is? It's an atom that has either given up or taken on what? Electrons. And now the atom has become charged, either positively charged, which is a cation, or negatively charged, which is a what? Anion. And ions are called salts or electrolytes, right? And they provide our electricity for our cells. And we are made of our what? Cells, right? So, we're learning. We're learning. We're doing great. We also know that there's atoms. Some atoms of elements will have a varying number of neutrons from the typical, and most of them are stable, and they're called what? But if they are unstable, they're called, and that means they're going to be giving off what? That's exactly right. All right, now you ready to keep going? Because you've learned the hardest part. Congratulate yourself, really. So that's the most about biochemistry. It's almost anything you ever need to know. Don't tell a chemist I said that, or let them listen to this recording. But do I have any questions? Do I have any questions? Okay. If y'all feel like this is really foreign to you, please either use the recording if I end up being able to do it, or notes from other people. Okay, so what I'd like to talk about now is I'll find it in all of these PowerPoints. And see, you can see these. I didn't make any of this stuff up, okay? I do want you to know about Marie Curie. Marie Curie, they called her Madame Curie. She received the Nobel Prize for her work with radioisotopes and with radiation. And so it's amazing that I consider this young. I know y'all don't, but it's amazing that she lived to that age, because her lab where she worked, and her daughter did live that old, and her daughter ended up following in her footsteps and working with radiation too, and died much younger of cancer. But her lab where she worked way many years ago is still so radioactively hot that you can't go in unless you're in full gear. She was working in there in a lab coat, right? So anyway, it really contributed so much to our understanding of radioisotopes and radiation, and how those radioisotopes can be used in diagnosis and in treatment. And a lot of other applications as well, like dating living organisms. Y'all have probably heard of C14 dating as far as that goes. That's kind of an old way to date things now, but it's still pretty good. Now, I've told you what ions are, haven't I? I've told you about electrolytes, and now the ones I told you about were just sodium and chloride. But we have many others. Y'all have all heard of calcium and phosphates, having to do magnesium, right? So y'all have heard of others. If you see something that has a little charge from its number, how about potassium, right? So y'all have seen these. You'll know they're a what? If they're positive, they're a cation. They're ions, aren't they? And if they're positive, they're cations. And if they're negative, they're what? Anions, exactly. And the significance and the balance of them is going to keep the electricity where it needs to be in our body for our systems to work. I want you to just have a basic definition for molecules, and that just means that two or more elements are coming together to play or not, okay? And I don't ask you this, but I think that it's interesting, so I do want you to know this. There are very few things that I will get you to learn the chemical formula for, but there will be a few, okay? So I want you to understand what you're writing when you're doing that. A molecular formula like this one, is just telling you how many atoms of carbon do you have here. Can y'all see it from where you are? I wouldn't be able to see it where from in the back, but can y'all see how many carbons are here? It's 2. And hydrogens are 6, and oxygen just 1, because it wasn't there. So if you look at the molecular formula, it's just telling you that. And actually, why don't you all write down right now for me, C6H12O6. Y'all write that down for me. That is the molecular formula for glucose, and I am going to want you to know it, okay? It's very few molecular formulas I want you to know, or chemical reactions I want you to know, but this is going to be one of them. So C, and I want you to just be able to recall it in your sleep. C6H12O6 is what? It's one molecule of glucose. That's exactly what it is. Now, just FYI for you here, look at this. This is so crazy. This molecular formula is equal to this one, but we see that these carbon and hydrogens and oxygens are playing in a different structure from one another. Even though they had the same numbers, they are playing differently, and that's the structural formula. And is ethanol anything like ether? No. No. So what did I just tell you? Structure dictates what? And look at this. Even at this molecular level, these are two very different beasts here, these molecules, and they're going to act very differently, and they act very differently because their structure is very different. So structural formula is important. You would never really, I mean, how many of you going into organic chemistry are going to become organic chemists? I didn't think so. So unless you are, you're never going to have to draw those or recognize structural formulas, but you understand that structure always dictates function. So having just the molecular formula doesn't always tell you what you need to know, because you would have to know the structural formula. Okay. Now, I never asked you all to help me come up with the molecular weight of a molecule. I told you how to come up with the molecular weight of an atom. Well, it's very elementary if I were to ask you, because what did I just have you write? I had you all write this, glucose, C6H12O6. You would get a periodic table, and you round those atomic masses. So carbon has, if we rounded the number on the periodic block that it's in, if we would round it to 12, there's 6 of them at 72, right? And that's how many hydrogens? There are 12 hydrogens. If you looked at the periodic table, you see 1. And so that means 12 times 1, you get it. And that's easy, right? I don't care. I don't care. But that's how you do that. But that's really, really easy. What I do want you to know, though, is this. I want you to know that there's 3 major types of ways that atoms will interact, if they're going to interact, if they're going to. And these 3 major ways that they do are going to be called that we're going to talk about: ionic, covalent, and hydrogen bonds. So write those 3 things down right now, and then I'm going to tell you about each of them. You ready? Oh my God. Okay. Wait a minute. Let me get to the one I want to get to first. Wow. That's so weird. Okay, that's fine. That's fine. I don't have a picture that I like. I want to have. Guys, the first one that you wrote down was what? Ionic. Good. If something's an ionic bond, what types of atoms do you think are involved in that? Ions, positive and negative ones. So that whole crystallized salt thing I told you about, that's between sodium and chloride that have gotten close enough together that they bonded well enough that they form crystals. So salts form ionic bonds, don't they? And they can crystallize if they get close enough together. But here's the thing I want you to know about ionic bonds. I can't believe I don't have a picture of that. Anyway, here's what I want you to know about ionic bonds. If y'all already know this, if you take salt and you put it into water, what happened to your crystals? What did that mean that they dissolved? What did that mean?
That they got their balance.
They separated from each other. You put that salt in water, you didn't lose any sodium or any chloride. They just, no, they just dissociated from one another. The water molecules isolated them out from one another. The water isolated them out. I'll show you how that happens in a second. If you were to take water that's had salt in it and you get rid of all the water, what will you have forming in the bottom? The salt back. You didn't lose any sodium and chloride. It's still there, but they became separated by those H2Os. They became separated. They dissociated in water. And that is the beauty of electrolytes and ionic bonds. The beauty of ionic bonds is that they're very weak bonds. If they weren't very weak bonds, we would be all crystallized. Do you realize that? But because we have water in our system, what do our ions do? They dissociate, and now they can actually do their electrical work that they need to do, right? If we become dehydrated and our electrolyte balance is off and any of that is off, it's going to throw off the electricity in our body, and that's going to be a problem, isn't it? But I want you to know that ionic bonds, this is what I want you to know about them, they're bonds between ions. And it's a very weak bond. I almost wish we didn't call it bonds. I almost wish we called that an attraction, because they are attractions between what types of charges? Opposite charges, and they will readily dissociate. Are you with me? And we are so thankful for that, because they dissociate in water. And now they've got their charges going, and they can do all kinds of work for us, okay? Now, what I want you to know is that, okay, I am just like so hating these pictures. All right, I want you to know about the second type of bond. It is called a covalent bond. Now, you already know what the word valent means. Didn't I tell you there's no such thing as a long word, a big word? You break it down and find something you do know in it. What do you know about valence? Outermost. If it's covalence, it means that these atoms must be sharing what? Outermost electrons. So these covalent bonds are sharing outermost electrons. Are we good with that? Yeah. All right. Now, there are two types of covalent bonds that you do need to know about. You ready? One of them is called non-polar, and the other is called polar. So I want you all to, when you write those down, I want you to really be able to think about these and make it intuitive instead of like memorizing anything. So I want you to think about something right now. When y'all think about polar north, and if you had a compass, what would happen to the needle of the compass? Where would it be pulled to? It would be pulled where? Polar north, right? It would be pulled to the north. There's magnetism that's pulling it there. Is that right? Mm-hmm. All right. So this is how we're using this term, non-polar and polar. That's how we're using it. A pull or no pull. If it's non-polar, there's no pull. It means that these cores, these nucleuses, these centers have equal number of positivity. So the electrons that are orbiting around each of them, that the orbits aren't being pulled to one core more than the other. Would that make sense to you? Because how could these be being pulled closer to here if these were equal? They're not. That's called non-polar, right? All right. Now, in polar covalency, though, and to me, I can just visualize this. The hardest thing about most people for chemistry, I think, is that they don't see. They can't see atoms, so they think it's all like made up. It isn't. You know, I can get where people think that, but it isn't. I want you to be able to visualize this, and then you own it if you did. This is oxygen, which has an 8+ core. And this little hydrogen only has a 1+ core. And this valence orbit of the oxygen is sharing with valence orbit of the hydrogen. But which of the cores has the biggest pull on it? The oxygen. So it's going to be slightly pulling this little electron, which is negatively charged, away. I wish they'd drawn it like that. You know what I mean? And so this hydrogen, by the way, there's another hydrogen right here. This little hydrogen takes on a slightly positive charge. This little hydrogen takes on a slightly positive charge. And this oxygen takes on a slightly negative charge. Now, they're not ions. They didn't steal or give away or take electrons. They're sharing them. But the overall, and listen to this part, the overall molecule, the molecule is now charged. So what I have just told you all, you've learned about charged atoms that gave away or took on electrons that became our electricity providers in our bodies. But now we're learning about polar covalency and realizing that molecules can become charged. This is a water molecule. It is a water molecule and it has become charged. Are you with me? Why? Because of what kind of very special bond? What's the special bond? What's it called? Yes, polar covalency. A water molecule, H2O, just one of them has a polar covalency, which means that entire molecule has a slight charge to it. The oxygen side is slightly negative. The hydrogens are slightly positive. Are you with me? We need to respect one. I mean, because of this polar covalency with water, it's the only reason that we know life exists on this planet. Astrophysicists, do you think they're looking for people or puppies on other planets and galaxies, or what are they looking for? Because what does it take for life as we know it on other places to exist? Water. And it's because water is a molecule that has this polar covalency that has taken on this slight charge the whole molecule has. Are you ready for that third type of bond? Are you ready for it? Yes, Aaron?
So with polar bonds, is the lesser, so is the hydrogen always going to be a little bit more positive? The lesser will always be more positive than the overall.
The one that's having electrons pulled away from it. See, the electrons are negative.
Okay.
So that's getting pulled away a little bit. And that's why it takes on the core is positive. Does that make sense?
Yeah.
Does that? Okay, because I get that question. I get why you asked that, like, why is it that? But since the oxygen pull the electrons to it, electrons are what? Negative. Yeah. Yeah. Okay. All right. Now, what was the third type of bond? Hydrogen. But that really shouldn't have been called a bond, and I'm going to tell you why. That really shouldn't have been called a bond, but it is an attraction, and it's so important. So I'm going to tell you why. By the way, the covalence, whether it's polar or non-polar, they're the strongest bonds we know. They're the strongest bonds, chemical bonds that we know of between atoms of elements. Atoms of elements that make up molecules. They're the strongest bonds we know. Was the ionic bond strong, or did it dissociate in water? Dissociated. It was kind of weak. Well, here I'm about to tell you the third type of bond called the hydrogen bond, and it's the weakest. Make sure you know it's the weakest of all chemical bonds, and it's the most important to understand physiologically. So are y'all paying attention? Everybody wake up 1 minute. All right? Because you're about to hear what these are. I want you all to just look up here and tell me what this molecule, don't look at anything else on here, but just this. What is that? A water molecule. What is that? What is this? What is this? Okay, y'all are over that game, right? So right now we have 1, 2, 3, 4, 5 water molecules that we see up here, right? And we said that these covalent bonds, it's a polar covalent, but these covalent bonds are so strong, they do not break, do they? They do not break. They don't. And they don't. Unless something extraordinary causes them to. And they can break. But anyway, just take my word for it. They're not. But then when there's quite a few of them together, all of a sudden, this slightly negative oxygen can cozy up to this slightly positive hydrogen. Do y'all see that? And they can form these hydrogen attractions. Do you get that? Because the hydrogen has a slightly positive charge. So they can rearrange and torque themselves until now there's this one. I'm water, and I've arranged a certain way, and I'm sort of touching, not touching, but I'm attracted to another water, and a water, and a water, and water. And yeah, everybody go this. Everybody do that. What just happened to the palm of your hand? It got warm, but it also got what? Why did it get moist? Because you had enough water molecules. You didn't have any more than you usually have when you do that, but you trapped them, and they got close enough together. And what formed between them? Hydrogen attractions, hydrogen bonds. This is why water stays together, is because of this. These water molecules stay together to form what you know of as water because of what type of attractions? Hydrogen bonds. And it's strong enough that water can be pulled from the root systems of sequoias hundreds of feet up to the leaves and the canopy of the trees. Because as these, if this is at the top of the canopy of the trees, as the air and the sun is breaking that water molecule off, that water molecule doesn't destroy it, it's just now in the air. But it broke it, and it caused tension on this one, and this one pulled up, and this tension on this is pulling this up, and it's siphoning it up from the roots of the trees. That's kind of beautiful, isn't it? Water molecules being held together by hydrogen bonds are tough enough that we have liquid water, right? At certain temperatures, we have liquid water. And it gives the properties to water molecules that we know of: adhesion, cohesion. As a solute, it is going to be the universal solvent. But because it is polarly covalent, I can drop crystal salt in it. And when I drop crystal salt in this, those attracted ions are now going to be dissociated. Now, I think I've got a picture of that, I hope, in a second. But they'll become separated, and sodium will be isolated down here, being surrounded by oxygen. And chloride, that's a negative ion, will be surrounded by these hydrogens. They'll surround it out and dissociate them. And they'll do that for any of those electrolytes on those charts that you saw. They dissociate them. Water is a universal solvent because of its polar covalency. Are you good with that? Okay. Hydrogen bonds, are they strong bonds? No. What did I just tell you they are? They're the weakest of all bonds, but I also told you that they're the what? They're the most important physiologically. Here's the picture I was looking for. You see, you had sodium chloride in crystal. You had it. You put it in water. But what ended up happening? The chloride got surrounded by these hydrogens that have an opposite charge, and the sodium got surrounded by the oxygens that have an opposite charge. It dissociated them, didn't it? Didn't get rid of them, didn't change them, just dissociated them. And this is going to allow for that type of solvency. The reason it's the most important physiologically, let's think about this. I tell you all, and I'm telling you now, so maybe you'll know it more later, but you'll hear me say it later. You'll think, yeah, I heard that before. Your cells are factories. They're factories that never get breaks. They're factories that will be told to up production or slow production, but they never stop. They don't take meal breaks. They don't take smoke breaks. They don't take phone breaks. They work all the time. Your cells are factories that are producing those organic molecules that I told you are necessary for the cellular life. Carbs, proteins, lipids, they're building those molecules. They're breaking molecules down. They're rearranging atoms to make other new molecules. They're working all the time. All the time. I forgot what you said. Let me take a break. Oh, But essentially, your cells are protein factories. Essentially, yes, they can make all those other things, but essentially they are protein factories. We're going to find out just a little bit, maybe not today, but from Tuesday, we're going to find out that proteins are those organic molecules that are the most diverse in their function that you have, and they're pretty darn amazing, and they make things happen at a pace that is almost unimaginable, that your cells can do things as fast as they can do things. If you don't believe me, can I give you just a little quick example? Proteins, and you don't write any of this down because we're going to get the basics of this. But proteins are made of amino acids, and many of you all already knew that probably. But you have 20 different kinds of amino acids that you need to build the proteins that you need. And to begin with building a protein, each amino acid has to come up one at a time to get on the chain. You can think of it as like a beaded necklace, or you can think of it as like a train with cars. But each amino acid has to come up and get in line one at a time. Proteins can have, depending on the protein, hundreds that are required to be on the beaded chain. Hundreds to make one protein. I want to tell you just an example about a protein called hemoglobin. Has anybody ever heard of hemoglobin? You know, it's an important thing that carries oxygen to our cells. It's not inside of red blood cells. It carries oxygen to our cells. One hemoglobin molecule has 4 chains that have hundreds of amino acids that have had to come up to get in line one at a time. Are you good at that? One hemoglobin molecule. One red blood cell has 280 million molecules of hemoglobin. That's hard to imagine, isn't it? Your bodies can make 2.5 million red blood cells a second. That's crazy, isn't it? Your cells are working all the time. Your cells need to have what they need to have to be able to function. They need to have those amino acids that end up becoming proteins. They need to have those building blocks that end up becoming the organic molecules that are necessary for the cell. They need to do it in the amount of time that they're supposed to do it in. Now, let me tell you something about proteins. The diversity of proteins, there's only 20 different amino acids, but how they come up, which one comes up and gets in line, and how they do that is called its primary sequence. But anyway, the structure of the protein dictates the function. The amino acids are held by a particular type of bond we'll learn about, but once they're in that chain, they will form because of hydrogen bonds. They will form their basic structure because of attractions in the bonds. Some of them will form ringlets. Some of them will be folded like accordions. Some of them will fold on themselves, but their structure dictates their function. And that macro structure is held together by what kind of bonds? And which are the weakest bonds? And if we add a little too much heat, so like we know hydrogen bonds hold water together, if we add heat to water, what will happen to those water molecules? The hydrogen bonds will break and they will let go of each other. We didn't break the water molecule, did we? We just broke the attraction between them, and they're still out there in the air. They were in our lungs when we did this and trapped them, right? And then they formed those attractions again. But hydrogen bonds are weak bonds. They're holding your proteins together. Don't do stuff that's going to mess up your protein structures, right? Don't get too hot. Don't get too cold. Don't take things that can break your hydrogen bonds for your proteins, because if you lose your proteins, you've lost their function, right? Your DNA, what do y'all know it's shaped like? You know, it's like a ladder that's been twisted. Y'all call it a foiled double helix, don't you? You know it's got 2 sides of that ladder with rungs, right? Those are really representing atoms, elements, right? We understand that. We're going to see what it looks like. But what you might not know is that recipes are held on the inside of the rungs, so that the whole molecule has to be able to open up so that the recipes can be read. What do you think is holding the strands of your DNA together? What kind of bond? Hydrogen. They will easily open up so that recipes can be read. That's a good thing. And then they go back together. It's hydrogen bonds, hydrogen attractions, which are the weakest of all bonds, but that's a good thing, isn't it? So guys, how many bonds did y'all talk about? 3 chemical bonds. How many did y'all have? 3. What was the ionic bonding between? Between ions, right? And the covalent, you had 2 types. What were they? Polar and non-polar. And which one is water? What type of covalent bond is polar covalency, right? That's what gives water, that whole molecule, its ability to do all those other things I just talked about, right? And this is why 2 water molecules can be attracted to each other. And what did we call that attraction? The 3rd type we talked about, which is a hydrogen bond. Are you good? Some of you got it. Some of you I can't read. You should play poker. And I don't know. But anyway, do you have any questions for me before we do lab? Do a little lab.
Can you explain the hydrogen bond again? I'm not really getting.
Okay. All right. Thank you. All right. Look. So, and this is the time to ask the questions. All right. So hydrogen bonds. When we think of a bond, let me preface it with this. When we think of a bond, we kind of think of this stuff when we think of bonds. But we said we understood that ionic bonds weren't really that. You were sodium, I'm chloride, and we're just cozied up, right? Because we're attracted to each other. You're positive, I'm negative. And so we're attracted. But it's tough enough that we can crystallize. But if we're put in water, we will be separated, right? That's ionic. When you think about covalent bonds, polar and non-polar, there really is a sharing. And it's strong, isn't it? It's a sharing, right? It's a sharing of those, and it's strong, whether it's polar or non-polar. Hydrogen bonds really shouldn't be confused about naming them that. They should really just be called attractions. And now don't write, just listen, Aaron, because you have the question. What I have found is usually the person asking the question all of a sudden gets so caught up in writing something they don't listen. Okay. I often have this. The person who asks the question about something at the beginning of the quiz, I'll give the answer. They'll be the one that misses it on the quiz, right? Not that time, but anyway. I'm just saying, just listen. So we know this is a water molecule that's got polar covalent bonding. Oh, and this is another one, and this is another. Hydrogen bonds happen, hydrogen attractions happen between hydrogens that are already in a relationship and a molecule, a polar covalent molecule, polarly covalent molecule. These hydrogens have taken on a slight positive charge. And so because of that, they're going to attract a polarly covalent element that is already in a relationship and has a slightly what charge? And it's just going to be an attraction between them. It's the weakest of all bonds. It should be called an attraction. It can easily be broken. It can be broken with a little heat. Y'all know that because you've left water to boil too long on the stove, haven't you? And what happened? It all disappeared. Where'd it go? You didn't lose any of these, but what got broken? These little bonds between a hydrogen that's slightly positive in this molecule attracted to this slightly negative atom in this molecule. That bond broke.
So they're just between
they're
covalent.
attractions between polarly covalent hydrogen and another molecule attracting to a polarly covalent negative.
Okay.
It's not always water. These are sometimes found between hydrogen and nitrogen that's attracted in other molecules. A polarly covalent molecule, though, like water, the whole molecule has become what? Charged. Your whole molecule of DNA is charged. And that's why when the strands get to a certain thing, a certain way and line up, there's only certain ways it can line up. But the attraction that's holding those rungs together is simply a what? Attraction. A hydrogen attraction. Can it be broken? Yes. The amino acids that got like a beaded chain, I usually have a beaded, the amino acids that got like a beaded chain, whether those beads are going to coil this way or fold this way is because of hydrogens that are in a relationship like this, causing it to torque a certain way. But it's weak. It's a weak attraction. And if you add heat to proteins, what happens to an egg when you put it on heat, on a pan? Does it look the same or did it change? It denatured, didn't it? That means it lost its shape. If a protein loses its shape, it loses its function in a living system. All right, is that good?
Yeah.
You sure? Yeah. All right. Anybody have any other questions before we take just another? Y'all want a quick break? Just another quick break. Yes.
I have a question about this like pretty complex. We're talking about electrons and membranes. How do we know when they how do we know that they're ions? Like,
Okay. All right. So you're not gonna have to really know. You're gonna see them, and you're gonna see them with a plus above them or negative, and you'll know that that's what that meant. They're ions. On a periodic table, because of their valence orbit numbers, they've been arranged in certain ways that you know. When you're looking, do you remember in chemistry you learned which ones were going to be which? Because of that periodic table, which is ingenious, by the way. Like, but people come up with the things they do. Right? It's pretty amazing. But you won't have to, I'm not going to ask you to know. I'm not going to pull something out of my hat and ask you, is that an ion or is that a neutron? I'm not going to ask that. I just want you to know what it means when you hear it. When you hear something's an ion, you know it either gave away or it took on valence electrons, right? When something's a neutral atom, you know it has equal number of protons and electrons, electrons. You know the definition of an isotope. You know the definition of a radioisotope, right? Will somebody remind me to please start with free radicals when we come back on lecture. Now this is going to be lab. We're going to do lab here in a second, but for next Tuesday, if somebody would remind me to start lecture with free radicals, explaining what free radicals are. Hey guys, and let me say this because I know everybody's excited. I've already had a couple emails about weather, potential weather coming in this weekend for Monday's. It was for Monday's class. I was having questions, but anyway, y'all, let me just tell you the policy of the college, and I have to go by this. The policy of the college is that, you know, if the college is open, you don't email me about what are we going to do about the weather and the college, because I have nothing to do with how they close the college. I have nothing. They don't ask us. They don't call me up and say how much snow is in your area, you know. And it's really hard because we live in a big, huge geographical area. So we can have some parts of our area that have dangerous road conditions, and then the other part of our region had none. You know what I mean? So it's really hard for y'all. I understand that. But here's what I'm going to tell you is going to happen for me. And this is what I'm going to tell you all so that you know. So everybody's listening, right? All right. So if the college is closed and they say that we're going to open like at noon, don't y'all come for just an hour of lab. Don't do that. Okay? I'm telling you right now, don't do that. Don't come driving y'all's distance for just that. If the college is open though, but your county's closed, if the college is open, I will be in here talking. I might just be talking to myself, but I will be talking and trying to record. If this college is open, I have a job, and I take that seriously, and I'm going to be here. And class is going to continue. But if your counties have closed their public school systems, you're excused. Did everybody hear that? Now, it doesn't mean that you need to email me and say what we do in class today, because I can't give you that lecture again. What are you going to have to do? And it doesn't mean that you don't need to be prepared the next time we come to class, because guess what you're going to have? A lecture quiz. So because I expect you, even though you didn't come and you were excused because of your county closing, you still have to be ready the next time you come in. Is that fair? That's like as fair as I can be, right? So, I mean, I don't know. If y'all tell me another idea, I'll consider it, though. Is that good? Yes, Jada.
So say we are excused when we come that Thursday. Will we have 2 visits?
No, I just won't use the quiz that you missed. It won't be a 0. You know what I'm saying? It won't be a 0. It just will be no grade there. That meant that you got exempt from that, if you will. But if your counties, and I get told which counties are closed, and that happens sometimes. We have that happen sometimes where counties, where I'll have some counties that didn't even go on delay, and other counties that were closed. I don't think, this class, I do consider this a really important class for y'all, but it's not life important. It's not like a thing you want to risk your life for. So, you have any questions? Did that make sense about the quiz thing? All right. So again, though, if they do a delayed opening, and let me say this, because this would be important for this class. If it's open at 10, come, because we'll be here from 10 to 1. But if it's open at 12, don't. Okay, just don't, because that's don't. All right, because some of you I know have things after this class, and you have to go to that. Did you have a question, Jake?
Yes, ma'am, and I'm not trying to trite you when I ask this.
Okay, I'll keep that in mind while I'm listening.
I don't know how many people lost power during the last thunderstorm, but we did.
Me too.
And if you don't know, like for the lecture, if you're going to try to give the lecture, or when school on this end of the county were to open, then what happens? Like I said, I'm not trying to try anything. I don't know.
I understand that, and they actually are they calling for significant snow this time too?
No.
No. Okay. So it depends. It's that fall line. See, we had this fall line that happens where some of us get it and some of us don't. It's weird. Our whole little area does have a very different kind of thing. They can have it. Okay, so what I'm going to say to you is that I feel like I get that about the power and the understanding of losing power, and I don't know. Let's just take that as it comes. Let's just try to take that as it comes and figure it out. But as far as being excused, if your county school systems have decided that they can't put school buses on the road, I don't want y'all on the road either. I really don't. So now I will be still, if the college is open, I'll be here recording. And we'll figure out how bad it is and how, I'll hear how much power outage there was and that sort of thing. And hopefully you'd be able to be ready. All right, so let's take a quick break and then come back to lab. The first thing we're going to do in lab is go over make sure you have the right answers in your practice. Okay? Those of you who missed, did you get to listen to the lab portion, the lab recording? It was only Janae, maybe, right? Did you?
Yeah, I listened to it.
You couldn't see what I was writing, so it made no sense, and you just gave up and you got frustrated, I bet. Okay, well, I'm sorry.
Well, she sent some notes.
She did. Did that help you? And this will help you because we're going to review it again. Okay.